Okay, we're going to build a bunch of circle properties today, and this video will show you how you do those discoveries and also summarize the 4 properties we're going to learn today. If you click on the link in below this video, I'll give you access to this document here, which has all the videos and the summaries of all the things we're going to discover, including links to a Desmos activity and GeoGebra demonstrations of what we are learning today. But we're going to start with the first circle property. So the first circle property, you actually are going to begin with the piece of paper, the small little circle that's been cut out for you. Okay, so this is when you're going to be folding everything. So you're going to use that circle that's cut out for you. And then you're going to click and watch this video here. So you're going to take your circle and fold it in half. This, of course, produces a diameter. If you take it again and fold it in half this way, we'll find the center of the circle. And you also, of course, have 4 radii. Now you're going to draw that radius on the original side, or the one side, and then fold it over so you get the other crease and draw the other side of that same radius from the center out to the tip or the edge. Now what you're going to do is take the bottom of this and fold it up so that the 2 lines will line up. So you're creating a chord and you fold it up so that they line up. Make that crease. That crease along here is a chord. Draw that chord along that crease. And then, of course, make your conjectures from here. But you can confirm that this is a right triangle by taking the corner of a page and seeing if it matches perfectly, and it does. And then you can also prove that this side equals this side by taking that same page and using it to mark off the distance, and see that it works out pretty darn good. So I was just really rushed, but here's one, the completed one with all the 1, 2, 3, 4 folds. Draw your line and your line, line it up, draw that chord, and check that the 2 bisectors, or that this is in fact a perpendicular bisector. So what we just constructed with that folding property is called the perpendicular chord property. And on your handout, then you can copy this theorem. A perpendicular line from the center of a circle to a chord bisects the chord. So it cuts it in half into 2 equal parts, and this is a 90-degree angle. The corollary is also the same. If this chord is cut in half, then the angle going, or this line going back here, must be 90 degrees. So copy that into your notes. And then you can watch this demonstration of this proof in general on GeoGebra. The property we're looking at is the right bisector of a chord. And you can see this looks just like the one that we have in our notes. And it says if you have any chord and you draw, cut it in half into 2 equal spots, that line from the midpoint to the center is perpendicular. Or if you take this perpendicular line, it will cut it exactly in half. And no matter how big your chord or small your chord is, or where that chord is on the circle, it will always be perpendicular and always cut it in half. And we can use that property in this scenario. For our second property and theorem, we're going to take our handout and go to the circle at the bottom that's got this diameter across it, and then watch this video. Okay, this one we have the circle with the diameter. And what I'd like you to do is pick any point on the arc of the circle, anywhere. It could be here, here, it could be even down here, but let's just do something above. So you pick any point. Then you're going to take your ruler and connect the spot from the end of the diameter to that point that you picked. I'll call that point P. And then the other end of the diameter to the point P. Looking at it, you might have any guesses of what conclusion we have, but it's this special angle up here that I'm going to say is 90 degrees. To verify that, you can take any piece of paper you want and just take it to the corner and see if you get a 90 degrees. And look at that, it fits perfectly. And so that's how you construct this second one property. So the property you discovered in this one is called the angle in a semicircle property. And you can write this theorem next to the sketch you just drew. An angle subtended from the diameter to a point is always right, or 90 degrees. So going from that diameter to any point on the circle, you drew one that was above, this one is below, that angle there is going to be 90 degrees. And now let's watch this demonstrated in GeoGebra. The property we're talking about is angles in a semicircle. And you see this is set up with the diameter and the points going from each edge of the diameter to any point on the circle. And you'll notice that that angle there is always 90 degrees. You can see that it's always 90 degrees no matter where we go. And so this demonstrates how the angle subtended from the diameter is always 90 degrees no matter where it ends up. Next, you're going to flip your handout over to the back, and you're going to look at this top circle with a little center. And then we'll watch this demonstration. For this third one, I want you to draw a chord in the bottom part of the circle. Go from A to B. It can be any length, doesn't matter. It's just easier if it's at the bottom. So we'll draw that chord. Then you're going to make two angles. We're going to make a central angle, which goes from the ends of the chord to the center. And then you're going to pick any point up here, anywhere on the circle. I'm going to pick it right about there. Doesn't matter, it could be anywhere. And now you're going to go from your chord to that point instead of going to the center. And of course go from both sides. So we have the chord AB going to the center, and then from the chord going to any point on the circle. The conjecture, the idea that you might be wondering, is about the size of this angle versus the size of this angle. You can make some guesses, but one of the things you might see is how this is smaller than this, and there might be a correlation. Here's the one, what I'm going to do. Grab your tracing paper or your parchment paper, and you're going to trace over this angle here. So just put it over top and then just do a nice trace. We're going to get that angle. If we compare it to here, you can see it's obviously not the same size, but instead of just also tracing one, I want you to move the edge of that little angle you just made to the other edge and trace again. So what you're doing is getting two of these angles. So there's one, there's two. So there's one there, and then do it again, and I get two. Now I'm going to compare that to the middle, and look at that. It's exactly half of this. So two of those fit in this middle one. So if this was X, this one would be 2X. Or if this was, say, 30 degrees, this must be 2 times 30, or 60 degrees. And it's proven here There's 1 and 2, and it adds up to that. And that is our third theorem. So what we just demonstrated with this is called the inscribed angle theorem. You can write this theorem on your handout. The measure of a central angle is always double the measure of the inscribed angle from the same chord. So if you go from this chord and go to the middle, or go to the inscribed, the angle in the middle is double this one. Or you could think of it as this as being half of that. Now let's watch this in general on GeoGebra. And we're looking at the angles at center. And we see here this is set up where the angle at the center is 100, and this angle up to the edge is 50. So this is double that. And regardless of where I drag this, you see that that angle stays at 50 degrees, always. And then even if I shrink this down into something smaller, let's try to go to 80. Oops. You'll see that the other angle is half of that at 40. And this is a demonstration. For our last one, you're going to go to the bottom of the page and use this circle that's blank, and then watch this video. For our fourth theorem, we're again going to start with a chord. I am just going to choose something here at the bottom, just randomly, and I'll connect it up. Have that chord. Then I'm going to choose a point on the edge of the circle. I'll call this P1. And I'm going to draw the lines from that point to both ends of the chord. And we have this shape. Now I'm going to pick a second point anywhere around here. Let's pick it maybe here, P2. And I'm going to connect it up to the edges of the chord. Now it makes us wonder about the size of this angle and this angle. They look very similar. I wonder if they're the same. Again, we can grab our tracing paper and go and trace this angle. So I have that angle, and I'll go around and swing around and notice that it's exactly the same as that one. And we have a fourth theorem, and that works no matter where I put a point. And just for fun, I'm going to do another one. Let's do it right here, P3. And I'll connect those edges. Back to the same chord. And I wonder about that angle. Well, if I bring this back and see that it's exactly the same as all of these angles. And that then is our fourth theorem. So what you just discovered, the angles subtended by the same arc theorem, and that says that inscribed angles subtended from the same arc are equal. Meaning if you have this arc here or chord, doesn't matter, and you go to one point and then go from those same endpoints to another point in the circle, those two inscribed angles are equal. Now let's go to GeoGebra and see this in general. You'll see I have this set up here, and we have the angle going out here is 30 degrees. No matter which angle I choose, if I have it going over to this point, it's still 30 degrees. It's always 30 degrees because it's coming from the same arc. If I change the size of this arc to get a different one, let's say 12.9, any point that goes to it are all going to be always going to be 12.9. So whatever the arc is, that subtended angle is going to be the same throughout. You can see that demonstrated here in Desmos. You see that I have an arc here going from here to here, and it's 30, and then somewhere else it's 30. And no matter which angle I choose, it's still going to be 30 for this specific arc. Now we even see the other property here about how it's double. The inside, the one that goes to the center, is doubled. But if you wanted to take away that, you could just see here, here's a defined arc, pick that point, and it equals, they both equal 0 no matter which one. If I make the arc, well, this is a defined one, doesn't matter how big it is. In this case, it's going to be 30. But if it doesn't matter how big this arc is, if I change that arc, I'm just going to get different angles. But every angle off of this arc is going to be the same regardless of where we go. And so here's a summary of the 4 theorems we just discovered. The first one, the perpendicular chord. It says if you have a chord here and it's bisected into 2 equal parts, this line going back to the center is 90 degrees. Or the perpendicular line, so 90 degrees perpendicular, from the center of the circle to the chord bisects it and cuts it exactly in half. The second theorem, the angle in a semicircle. The semicircle is created by the diameter, and any angle that comes out from that diameter is 90 degrees. The third is the inscribed angle theorem, and that says if you take any chord or arc and take that point, or from each edge of the arc to the center, that measurement is double the angle that's created when you go out to the edge of the circle. And no matter where this goes, this angle here will be half of this, or the measure of the center is double the inscribed angle. And finally, the angle subtended by the same arc, a similar idea. 2 angles coming from the same arc, but going not to the center this time, but going to the edge of the circle. Each of those is going to be equal to each other, no matter where that point is on the circle. If it's coming from the same arc or the same chord, it's going to get you the same angle. And there's the summary of the 4 theorems we learned today.